Thanks a lot, Wilfred, for your introductions, and thanks for everyone to be here. It's a very unusual timing, of course, and thanks for inviting me to give this talk. I will talk about coagulation-fragmentation equations, and you can see that it's sort of fit into the framework of mean few games in a broad sense. It is not really mean few games, but I will tell you that it is certain mean fields model, and at the end of the day, we're gonna come to essentially the same general themes of research. You're gonna see throughout my talk. This is a joint work with a PhD students, Truong-Son at Carnegie Mellon, and we have been working on this since last year, and it's really fun. So I want to share some of the ideas and sort of research with you. So let me start here. So I describe right away to you this so-called coagulation-fragmentation equations. So basically, you can think of C as a sort of density. So it represents the density of clusters, where S is greater or equal to 0 is the size of the cluster of the cluster, and then C of ST represents the density, the total number of clusters of particles of size S greater than or equal to 0 at times T greater than or equal to 0. What you can imagine that you have certain sort of number of clusters of clouds sort of hanging around at time 0, and then you let time starts, and then those clusters sort of start moving and interacting with each other, and we have a coagulation-fragmentation equation comes out from that. And you see that I write down right away the equation 1 there. So 1 essentially is saying that the change in time of C is the sum of two quantity, where Q of C with C is the so-called coagulation terms, and Q of F of C is the fragmentation term. And I'll describe to you, basically for this equation, there are essentially two effects. It's sort of like kinetic type equation. It has the first effect of different clouds joined with each other. So that's the coagulation effect. You can see it here. So coagulation represents the binary merging of two clusters. So for example, you have a cluster of size 1 merged with a cluster of size 2, then you have, a cluster of size 3 forms, and then the other two disappear. And then there's the other effect called fragmentations. That is the reverse one that sort of constantly, at a random time for a random sort of cluster, it can be broken into two small clusters. So you can think of them as sort of like clouds in the skies that certainly they can merge together to create a bigger cloud size, or they can sort of be divided into smaller cloud size. And here we are only talking about binary effects, because we are essentially saying that, okay, you can have more than two clouds, or a lot of the clouds joining together, but the chance for that to happen is literally 0. So we are only concerning about binary effects. So I have binary merging and binary splitting. And also here that you see that it's simpler than kinetic equations, in the sense that I'm not taking into account the positions of the clouds as well as the velocity field of the clouds. So you're gonna see why. The short answer to this is that we are trying to simplify and consider some simple enough model to analyze the problem. Okay, so that's that. And also here I'm considering only the continuous model. So by that I mean that I only consider the cloud size to be any time. Be of any size S greater than or equal to 0. In the literatures, we can also consider the cloud size of size of natural numbers, for example, or discrete, and then we can also do the mean field limits to pass the limit. But for here, I'm only considering already the mean field model with continuous density. Okay, so that's sort of the short description of the equations. Now let me sort of giving you a more intuitive explanations of the two effects. So the first thing is the so-called coagulation term. And a lot of you here maybe have been working with sort of sticky particle system, then you can see that there's clear similarity between the two here. Essentially, I have sort of two groups of two clusters, two groups of particle, one with X amount, the other with Y amount, and they meet with each other randomly, supposedly, and then if they meet, they create a bigger cluster of size X plus Y. Okay, so it's a very simple effect, and you see that again, as I said, we are not taking into account the positions of the clusters as well as the velocity field. Here, everything is taken into account through the kernel. So AXY is the kernel, which represents the rate of coagulations or combinations between X cluster and Y cluster. And depending on certain models in practice, A can be different, but in general, A is symmetric and, non-negative. Again, in different areas and different perspectives, and A can be different. For example, I was told that at UW here, there's a group of people working at the agriculture department where they also study this kind of equations, where they handle studying sort of the formations and the homogenization of the milk. But I've never talked to them. Okay, and then there's the other term called fragmentation term, which sort of like going in the same way that randomly at certain rate, if you have a cloud size of size X, it can randomly being broken into two smaller clusters of size Y and X minus Y, and we represent this kind of fragmentation terms by a kernel B. B of Y and X minus Y represents the rate of fragmentations of a cloud size X being broken into two smaller sizes of Y and X minus Y. So those are the two clear effects of the equations, and you can see that everything is being simplified and being sort of like coupled into the kernels A and B. So essentially, A and B contains sort of all the sort of physical aspects of the equations, and again, depending on different model, A and B are different. And for today, I will focus on just one case of A and B. You're going to see later. Okay, now if we know those two effects, we can write out the PDE or the equations very, very quickly. You can write out the coagulation kernel, and you can look at the first two lines here. That I have QC of C as S and time T. How do I write it down? Well, I mean, if we remember that to form a clusters of size S, I would need to take a clusters of size Y and a cluster of size S minus Y combining together. And you see that that's exactly the first term, right? I'm taking a clusters of size Y multiplied with a clusters of size S minus Y. And for that to happen, the rate of happening is A of Y times S, A of Y comma S minus Y. So that gives me the first term, the integral from 0 to S of that term. And I have to divide by 1/2 because I'm doing double counting, right? Y and S minus Y is being double counted. So I take 1/2 of that. So that's what I get by having clouds of smaller size combined together to create clouds of size S. And on the other hand, I'm also losing things, right? Because I'm having clouds of size S combining with clouds of size Y to create a bigger clouds of size S plus Y. So you see that the second terms over there, minus CST, the integral from 0 to infinity of ASYCYT dy is what I lose. So, so I get that amount and I lose the other amount. So that gives me the coagulation term. So it's sort of surely integral non-local term. And the second term is the fragmentation term. You can see that we can also do it in the same way, that I count the amount of cloud size that I lose, that S is being broken into S minus Y and Y. So that's the first term, minus 1/2 of that. And the second term is what I gain, right? Because I have a class of bigger size, Y plus S, that is being broken into S and Y, and that's what I get. And the coagulation-fragmentation equation is essentially the red one down at the bottom. I have CT is equal to QC plus QF. So that's the equation being written in this form, which is clear. This is sort of surely the classical form of the equation. So a very brief literature. I must say that this is a huge field with lots of important results, and I cannot describe everything in just one single slide. So if I omit some literatures or some references here, please forgive me. In our paper, we have more. But basically, if there is no fragmentation term, there's only coagulations, meaning that things are combining together to make things sort of a bigger size. Then this is essentially the Smoluchowski equation, which is very famous, that was written down about 100 years ago. And also, a special case of coagulation-fragmentation equation is the so-called Baker-Doring equations. That is the type of equation in a discrete sense where you only have clouds of size n being broken into n minus 1 and 1. And also you can only combine clouds of size k with 1 to have k plus 1 cloud size. Okay? And I list to you here a bunch of amazing and important results in the literature. It's both in physical context and also in physics and also in mathematics. And the rigorous treatment of those equations, you can see, probably started from the paper by John Ball and Jack Carr in 1990. And it appears in both PDE and probability context. For example, there's a great survey by Davis Aldos at Berkeley. And also there's two very important papers that is related to our work. There's Escobedo, Missler, Patam, Escobedo, Laurensois, Missler, and Patam. And also the next one is Menon Pego that we're going to use. Okay. So it's incomplete, but it shows that this equation has quite a long history. Now let me go to the next slide. So our main focus for today is that we're going to focus on only one particular case, which is the critical case. I'll tell you why is it critical. But let me say it out loud right away that we are considering the case where the coagulation kernel is multiplicative, which is that I have A S S hat is equals to S times S hat. And the fragmentation kernel B S S hat is always constant. Okay, I'll explain a little bit more why is it the critical case later on. But one of the main features that makes this equation extremely interesting, at least in my taste, is that everything is physics terms, that sometimes the system might not conserve the mass. And this can happen because of two different phenomena. The first phenomena that can happen is the so-called formations of particles of infinite size. So basically you can see that, if coagulation happens too quickly, right, you have sort of particles or you have clouds of small size, if they keep merging really, really fast, then after a finite amount of time, you can imagine, right, like for example, after 1/2 time, I have one join with one to create two, and after sort of 1/4 of time, I have two join with two to create four, and so on and so forth. So maybe, in a combinatorial way of thinking, after time 1, we can create really clouds of size infinity right away. So this is happening when coagulation is very strong. And as I said, for example, at the direct department here at UW, there's a group studying this because they were saying that, if you take sort of non-homogenized milk, they would try to study sort of this sort of thing, then gelation does happen. That's saying that, suddenly there's sort of concentrations of some other stuffs, maybe cheese or something. Or the other way that it can happen is the so-called formations of particles of size 0 or dust formations. That's the reverse situation is when fragmentation is really strong. So when it's really strong, it's sort of like fragmentate the clouds, right? So the clouds being sort of making smaller and smaller and smaller really, really quickly. So after a finite amount of time, you create sort of a bunch of dust. So you lose a bunch of mass, which is basically particles of size 0. So you lose a lot of them. And still the system is physical, but it's just that you lose mass. It's typically the case in the literature of this field is that if we know coagulation is stronger, then it's easy to be handled. Or if we know that fragmentation is stronger, then also we know how to handle it. So the most complicated case is the case where the two are of equal strength, right? Which is a critical case, and this is why we are really interested in that. So in this critical case, it's a very, very particular case that we are interested in. Is this when A is S times S hat and B is just 1 for all time. Okay, so I just explained why we are really interested in that, and then so I guess I can explain next is that instead of also, if you look into the equations in the classical form, you can also look at the weak form. Like we all at some point when we want to do things, then we can write out the weak formulations of our PDEs and try to do integration by parts. So this is exactly that, right? So if you plug in any test functions, here I wrote that it's sort of bounded Lifshitz with 0 at 0. Then what it means is that if you plug in the test functions, you have the change of d over dt of the first integral equals to 1/2 of the second integral minus 1/2 the third integral, and that's the form. But let me explain why. So sorry, it's just hard for me to explain because my pencil doesn't work here. But the right hand side has two integrals. The first integral represents essentially the coagulation term. You see that you lose particles of size S and S hat, so that's represent for phi S and phi S hat, right? And you gain particles of size S plus S hat, so that's why you have phi S plus S hat minus phi S minus phi S hat. And then because I assume that my coagulation kernel is S times S hat, that's why I have S times C times S hat times C. Okay. And the second term of the integral on the right hand side is representing the fragmentation term. So it goes in the same way, because it being fragmented, so I lose particles of size S, but again particles of size S hat and S minus S hat. Okay. Of course, why do we care about this weak form? If you write out this weak form, you stare at it for, like a few hours, let's say, then we see that, we should utilize this weak form in some ways. And clearly, because I have some certain additive structure over there, I have phi of S plus S hat minus phi S minus phi S hat. So maybe naturally, it's good for me to take test functions to be polynomials, for example, right? Those are natural for me to read up information, let's say. For example, I'm going to do it in the next slide, but you see that if I take phi to be 1, for example, then the two terms involving phi on the right-hand side are going to be both minus 1, right? Because it's just like, or if I take phi to be linear, if I take phi S to be S, then, the two terms on the right-hand side just going to be 0 automatically. Okay, so that's exactly what I'm going to do. So let's do some formal computations. So here, let me say that to make things rigorous, I need to take test function to be bounded. But I mean, because we are doing formal computation, so I can just take anything I want. So the first thing I'm taking is exactly Vs equals to S. And if I take Vs to be S, then you see that I have exactly the first momentum, which is the total mass, right? So it's m1 of t. Why? Because I have CST represents the number of particles of size S multiplied with S, gonna give me the mass, and integrate. So that's gonna be the total mass of the system. And formally, if I take Vs to be S to be the test functions, if you look back here, the two terms involving phi on the right hand side equals 0. So that's essentially give me the fact that I have conservation of mass, right? So that's one of the key things that people care about. But of course, this is formal because I don't know whether it works or not. Because again, phi is the test function I took is not bounded. But anyway, it's a good start. It gives us some intuitions about things, right? And similarly, you can define the kth moment of the system to be just integral from 0 to infinity as to the case of CSTDS. So that's the kth moment. And, formally, you can do computations with all the kth moments that you would like. You can do computation with second, third, and fourth, and so on moments. And most of the times the system is not closed, so it's a little bit hard to read off information, but sometimes we are lucky. And now let me do also the next formal computations, which is taking phi to be 1 to be the test functions. Okay, so you can see here that this is also formal because phi doesn't satisfy my condition. So phi is bounded here, but phi is not 0 at 0. But again, I as I said, we can always do formal computations to compute. So let me go back to the here. You see that when I plug phi to be 1, the two terms on the right is just going to be -1, right? So that's exactly what I wrote it down here. And m0 here, the 0 moment represents the total number of clouds or total number of clusters at any time. And you do computations, you see that the two terms on the right can be simplified, right? I mean, the two terms on the right, the integral of ST times S hat C S hat T, that's just going to be m1t squared, right? So I can write down that m0 prime of t equals to 1/2 times m1 times 1 minus m1. And this is an important point for me to read up informations, because I see that, assuming that my system have conservation of mass, saying that m1 of t is always m1 of 0 for any t, then I can see here that if I start with m1 of t, the total mass greater than 1, then the right-hand side is a negative number, right? So the right-hand side is a negative number. That means that m0 gonna be negative after some time. And you see, if it's negative after some time, then that means that I don't have any cluster anymore after some finite time. That means that I should have some sort of, after some finite amount of time, I just lose all of the clusters. So that means that I lose conservation of mass, right? On the other hand, again, heuristically, if I have that m1 of 0 is between 0 and 1, then it seems that things are fine. I have the number of clusters are being increased, but I'm not running into any contradictions. So that's just that. And it is believed that 1 is exactly the critical mass. If you're bigger than 1, then you're going to lose mass and you're going to run into trouble after some finite time. But between 0 and 1, you should be fine. Okay, and that's exactly what was done by Bergeron and Giff, or Escobedo, Missler, Pertam, Escobedo, Lawrence, Missler, and Pertam. and through their works, they give a very sharp conjecture for this kind of problem. That if your initial mass is between 0 and 1, then the system has a unique mass conserving solution for all time. This is for all time, not just for short time. And then if your initial mass is greater than 1, then there are going to be no global mass conserving solution, which means that after some finite amount of time, you're going to lose mass. And I actually show you the two heuristics, but very important computations that those people did. It's amazing. So we are interested in working on this problem, and so far, before our work, all of the works, in this coagulation-fragmentation equations, essentially involving with doing moment bounds and do it heuristically using inequalities to bound the moment bounds, and then you try to bootstrap and try to do rigorous computations out of that. And here are some works. Here is sort of like the case that the initial total mass is greater than 1, and then with some additional assumptions, for example, the zero moment is finite, then Banasiak, Lam, and Laurent-Schwab proved that there's no global mass conserving solutions. And then from 0 to 1 was open. Laurent-Schwab could prove that if your initial mass is small enough, it's between 0 and 1 over 4 log 2, then and with some further higher moments conditions on the initial data, then you can prove that there's a unique mass conserving solution. Again, those are based upon moment bounds computation and results. Okay, now let me change the mode. I'm gonna try to formulate the problem in a different way and switch to really Hamilton-Jacobi equation. Again, if you look into the equation, coagulation-fragmentation equation, right? There's nothing about Hamilton-Jacobi, but surprisingly we can do it. Okay, so here we go. So as I said, the natural candidate for us earlier to do was to use polynomials as test functions, and then of course if we think a little bit more about that, we say that okay, if we do polynomials, and we can combine polynomials, and then if we can combine polynomials, then exponential function is a natural candidate, right? So it turns out that this is exactly the case. We can take test functions Vs to be 1 minus e to the minus sx to be test functions, and then we use it as a test function and define xt to be this integral from 0 to infinity 1 minus e to the minus sx times cstds. And if you look into this a little bit without the 1 there, then it's exactly Laplace transform, and we have used Laplace transform a lot in solving ODEs and stuff like that, right? This is a little bit different with 1 minus e to the minus sx, and this is according to the paper by Bob Taylor and Garvin Manor. They say that this is earlier they said that this is sort of generalized Laplace transform, but then it comes to the name that this is Bernstein transform. So we're gonna use this transform to transform from the non-local integral differential equations into a certain PDEs that we can analyze. And there's a key magic point here is that if I use this one as a test function, you see the combination terms that I use a lot is phi of s plus s hat minus phi s hat. With this test functions, and I can use one magic point here. This is then equals to actually minus phi of s times phi of s hat, and this is a magic point that helps me to write this sort of complicated difference term in terms of the product term, right? And then with this taken into account, and take this to be the test function. Let to be the Bernstein transform of C. I can write out a PD for my problem actually. So you can see that it's actually not so hard to do. This is sort of like maybe it takes us a few hours, or I don't know. It's certainly not easy, but it shouldn't be too hard. That we use that transform and we can write the a Hamilton-Jacobi equation out. Okay, so I have this equation. I'm not going to read it because it looks a little bit complicated. But anyway, when we see this equation, then it means that it's good. We can, instead of analyzing the coagulation-fragmentation equation, we can move into Hamilton-Jacobi equation and analyze it and try to read off information back to coagulation-fragmentation equations. So here, there's still a term M1T, which is the mass at time t, which is hard to study. So what we're going to study is that we're going to try to do sort of deductions by assuming that we always have conservation of mass. That means that we always have that M1T equals to M for all T. Okay. If we have that, then I can write down my equations to be the 2A, 2B, 2C over there. So I have a very nice sort of quadratic Hamilton-Jacobi equations. I have ft plus 1/2 fx minus m times fx minus m minus 1. So that is just a very nice sort of quadratic term from Hamilton-Jacobi equations. But then I have a singular terms, which is f over x minus m equal to 0. Okay. I mean, it's singular, but still, it looks nice. And I have a certain bounded conditions that f is always bounded between 0 and mx, I'll explain why. And surely I have initial conditions. Fx0 equals to f0 of x. Okay. So let me explain a little bit about boundary conditions and certain conditions here. And then I'll tell you what can we do. Okay. Okay. So first about boundedness, you see that f is always greater or equal to 0, of course, because C is the density, is non-negative. It is bounded between 0 and mx because you can see that the inequality I wrote it down over there. I have 1 minus e to the minus sx is less than or equal to sx. So using that, and remember the fact that integral of s times cs dds is just m, which is the first moment. So I have the bound, which is mx. And then I can also use the dominated conversion theorem quickly to see that the solutions to the Hamilton-Jacobi equation has to be sublinear in x. So it's bounded between 0 and mx, but as x goes to infinity, it has to bend down. So it's sublinear. So that is a natural thing. So we are in business because now we can study this singular Hamilton-Jacobi equations given sort of boundary conditions and given the fact that the solution is sublinear in x. Okay. So let me tell you our results and then I'll try to describe some ideas. Okay. Before that, I said it already, but let me emphasize again that the equation is singular at x equal to 0. And by analyzing the equations a little bit more, we see that it has two special solutions, mx and m minus 1x. Both of them have linear growth except when m is 1. And this is important because it tells us that those special solutions actually are not physical, right? Because those physical solutions have to have sublinear growth in x. Okay. So here's our results. For Hamilton-Jacobi equations, again, lots of you here are top experts in the field. You can see that although it's singular, but it shouldn't be too hard to study wellposedness of the equation. So I wouldn't say that this first result is surprising. It's rather standard in the field. Is that if m is bounded between 0 and 1, and if f0 is Lipschitz and sublinear, then the Hamilton-Jacobi equation has a unique Lipschitz sublinear solutions. So that's normal. Why is it the distinction between 0 and 1 is important here? It's because of the fact that it has two solutions, mx and m minus 1x. So if m is less than or equals to 1, then the second solution, m minus 1x, is less than or equal to 0. So that is a very important threshold for us to have a sublinear growth solutions. Okay. But what is important here is the corollary that we can conclude now is that in the range from 0 to 1, the coagulation-fragmentation equation had as most one mass-conserving solution. So that gives us that we have uniqueness results from 0 to up to 1. Right? Because we have uniqueness of the Bernstein transform. So if we have two solutions of coagulation fragmentations, we do Bernstein transform, they have to be the same. That means that the other two solutions have to be the same. Okay, so that's our first result. The second result is the other range, that if m is greater than 1, then we can prove that we do not have one solution to our Hamilton-Jacobi equations. This is quite interesting, but the proof is also not too complicated. The key point in this analysis is that we see that the two special solutions are mx and m minus 1x. Because m is greater than 1, so both of those two special solutions are positive and are having linear growth, and they force us not to have any C1 solutions that is sublinear. Because both of that are having linear growth and bigger than 0. But again, what is interesting also for us is that we can conclude then that if m is greater than 1, then there is no mass-conserving solution to the coagulation-fragmentation equations, and I hope this is optimal. Earlier, there was already the results of Banasiak, Lam, and Lawrence-Wa, but they need to require more. We only here need to require essentially the only minimal assumptions that the initial mass has to be bigger than 1. Okay, so far we have uniqueness in the range from 0 to 1. We have non-existence of solution in the range from 1 to infinity. So what is missing is the existence of solutions from 0 to 1. And that's our next result. So surprisingly, for existence, we only have it up to the range from 0 to 1/2. So we show that if m is between 0 and 1/2, then we have existence of solution to coagulation fragmentation equations, and we are still missing the range from 1/2 to 1. Okay, so let me explain to you why. Because we have shown that there is a viscosity solutions, but that's not enough. To have existence of solution to coagulation fragmentation equation, we need more, and that's the key point. So let me go to the next slide to illustrate this. So it's hard to have existent results here because we look back into the Bernstein transform. F is of this integral, and it turns out that you can differentiate F as many times as you like, right? You can differentiate n times, for example. If I differentiate n times and I have that quantity, I wrote it down there, it's well defined. And it's even have a sign, right? I have minus 1 to the power n plus 1 of the nth derivative of f is always non-negative. Therefore, to prove existence of solution to coagulation fragmentations, what is really, really hard here is to show that the viscosity solution is C infinity. And furthermore, not just that it's C infinity, it's sort of changing signs in the derivative. And this is, in the literature, the people call this one sort of, suddenly I forgot the name, monotone functions. Never mind. I need to show that f is positive, f prime is negative, and f double prime is positive, for example. So I have to show that it's sort of, I take it back. I have to show that f is positive, f prime is positive, f double prime is negative, and so on and so forth. So the signs have to change. And this is where it's getting really hard because we know that most of the times viscosity solutions are only Lipschitz. To show we have regularity, and in this case to show that it's C infinity, it's amazingly hard. And that's why we have so far have only been able to get the results up to the range from 0 to 1/2. and not more. Okay. So I guess I have 10 minutes, which is good enough for me to tell you our strategies. So here's our strategy. Okay. So the hardest step turns out to be proving that F is C11. Once I can show that it's C11, then I can bootstrap to show that it's C infinity, and then, C infinity is not hard. And then the next step is also hard, but the hardest step is C11. You can see that there's some relation with Alpa's talk yesterday. That, once you have C11, you get to C infinity. So to prove that it's C11, I'm adding viscosity, and then I'm trying to get uniform bounds with respect to epsilon, independent of epsilon, of course. But what is weird here is that I'm adding this viscosity, which is not a normal viscosity. So adding normal viscosity wouldn't work. I will explain why. So we need to add the viscosities, right? In the sense that I need to add Ix to be X. So it's sort of degenerate at 0. And, for bigger H, it's just constant. That's not a problem. So it's sort of like increasing from 0 and then sort of bending to a constant 2, from 3 to infinity. And I will need to sort of extract uniform bounds here with respect to the gradient and the Hessians of epsilon. So what we got here is that the first type of estimates is not so hard. To prove that epsilon x is between 0 and m, it's just maximum principle. And you can see that this is a quadratic type PDE. So, in general, if you have a convex, quadratic, whatever, general convex Hamilton-Jacobi equations, you can prove that your solution is semi-convex and concave, And in this case, actually, we can prove that epsilon is concave. That's not hard. It's just maximum principle. What is really hard is to prove the lower bound of epsilon xx. So how did we prove the lower bound of epsilon xx? So what we consider was to, try to use the maximum principle for x times epsilon xx. And we show that this is greater or equals to -1. Okay. I'll also explain why we have to take x times epsilon of xx. If you look at here, the viscosity terms is also like that. It's x times epsilon of xx. Okay. So what is really hard here is that, we have this one, and then we try to write out the maximum principle for that. And by careful calculation, it turns out to be that if we let alpha to be the minimum value, then alpha satisfies a quadratic sort of equation type inequality, right? So I have alpha squared plus a alpha plus b greater than or equal to 0. Then of course it can happen two ways. It can happen that either alpha is greater than or equals to the big solutions, or alpha is less than or equals to the smaller solutions. And then we have to use the continuity method here to omit the other range. So we conclude that alpha has to be bigger than or equals to -a plus root of a squared minus 4b over 2, which is greater than or equals to 1. And here's the point that we need to use the fact that m is between 0 and 1/2 is where after careful calculations, we have to use the fact that delta, which is a squared minus 4b, is greater than epsilon, provided that m is between 0 and 1/2. So here we have not been able to get to the other range, the bigger range of m between 1/2 and 1. Okay, so again, I'm cheating a lot here. I mean, this is sort of the hardest step in our analysis, but I don't have time, so I'm just telling you sort of in a minimalistic way how we did it. And the next steps is not hard. The next step is going from C11 to C infinity. This is just by using Hamiltonian system. We write out the Hamiltonian dynamics here. And you can see that because M is C11, of course, characteristic cannot cross each other. And so this is 1D, so they are well ordered actually. And furthermore, you can see x dot is pt minus m plus 1/2. P is surely the gradient of f. We have shown that the gradient of f is between 0 and m. So you see that x dot is actually going to be always smaller than minus 1/2. So that's why you see that the characteristics are going sort of like from the right to the left. So they are decreasing. They're really well ordered. And by using the fact that it's C11, we can prove that, you know, the characteristic lines give us the diffeomorphisms, sort of like transforming any interval to any interval in the smooth and diffeomorphism way. And from there, we can get C infinity. So that's not hard. And now the last step is that from C infinity, we have to show that the derivatives are sign changing. And to do this, you know, it looks complicated, but essentially we look at the quantity x to the power k minus 1 times the k derivatives of f, and we are analyzing along the characteristics. We write out very complicated equations. We differentiate as many times as we wish. We write out complicated equations, but because we have localizing effects from Hamilton-Jacobi equations, so we only have to understand and analyze these equations among the characteristic and localize them, and, you know, use the maximum principle in a sort of clever way, yeah, to get the result. This is okay. I mean, it's so I would say that the hardest step is the first step, and so far we only have been able to go up to 1/2. Now, in the last 3 minutes, let me explain to you the key idea why. Why did we choose this kind of scaling, a weird kind of scaling? Why did we choose x times fxx, or x to the k minus 1 times the k derivatives of f? Okay, so this we got the intuition actually from the Bernstein transform. Because if you write down the fxx here, it's going to be s squared times e to the minus sx times c st dt, ds, I'm sorry. And we ask ourselves, what's going to be the correct scaling? And actually, this kind of critical scaling comes all the times in the equations, because there are two competing effects. And it turns out that the correct scaling is going to be x times fxx. Why? Because if you multiply x in, you're going to have that, I put everything in blue there, is that I put it like sx times e to the minus sx. So that one is nice and well controlled. And then the other term is s times c st of ds. S times c st ds is essentially the first moment. So that actually gives me the correct scaling. And it's also the reason why in our analysis we have to deal with the w there, which is x to the k minus 1 times the k derivatives of f. And this is why it makes the problem a little bit complicated. I didn't say it from the beginning, but it makes the problem a little bit complicated because we have to deal with a certain degenerate type of the equations, right? Because when we add the viscosity, we have to add like x times fxx. But it's just because of the nature of the PDE. I mean, we tried to do it by using different viscosity. It just didn't work. We have to really respect the critical scaling here. Or maybe we are missing something. I don't know. But that's that. Okay. So that's good. I'm on time. So let me just conclude now is that so far we have uniqueness for the full range from 0 to 1. We have non-existent of solution for m greater than 1. Existent we only have from 0 to 1/2. So we are missing a range of existent of solution from 1/2 to 1. And this is corresponding to the fact that we already have the viscosity solution to a singular Hamilton-Jacobi equations. What we need to do is to show that solution is smooth, and that's hard. We have not been able to do that. And also, you have seen that we should be able to understand deeper optimal control theory hidden here. You have seen that I have written down here a Hamiltonian systems so far we have not understood this one very well. Maybe there's some magic tricks hidden here that we should be able to utilize better, but so far we have not been able to do that. And finally, lifetime behavior results. That's important. We have a recent paper with Yoshimitake and Sun Van. We just finished it. Anyway, thanks for your attention.